Οπότε πάω και εγώ στη θέση μου.
Ποια είναι η θέση σου?
Στο υπόγειο. Κάνω την ηλεκτρική αναμετάδοση.
Ωραία.
Εντάξει.
Τι χρειάζεστε? Εγώ θέλω...
Καλημέρα σας. Καλησπέρα.
Γεια σας, γεια σας.
Is everything okay?
Is everything okay? Is everything okay?
Ακουγόμαστε.
There is an echo.
Καλησπέρα σε όλους. Ακουγόμαστε?
Εγώ σας ακούω μια χαρά.
Μάλιστα, πολύ ωραία. Πολύ ωραία. Γεια σας κύριε Χαναμουδάρη.
Τι κάνετε?
Καλά, καλά εσείς. Καλά,
δεν ξέρω τώρα αν είναι. Μήπως να κλείσω την κάμερα, δεν ξέρω αν είναι καλή ιδέα τώρα.
Θα έλεγα μόλις ξεκινήσουμε την λήψη με συγχωρείτε, μόλις ξεκινήσετε. Good afternoon. We will be starting in a few minutes. Here we are together with Mr. Hazadonakis. Hello. The General Consul in Johannesburg. We are about to begin in a few minutes.
Έχεις επιστροφή, από πού? Γιατί έχεις επιστροφή?
Can you hear us?
Manoli?
Κύριε Χαρμανδάρη.
Maybe we call me Vasilis, first of all, I feel. Maybe we want to do a test to make sure that I can share the screen or something.
Yes, please let me make you co-host.
Yeah.
Okay, you are now co-host. I will also make Mr. Taylor. Good afternoon, sir.
Hello, Mr. Taylor. How are you?
Well, thank you. Good afternoon to you.
Nice to see you from Greece.
So if I do that, you should be able to see my screen, right?
Yes, yes.
And now the whole presentation.
Perfect.
Screen.
Perfect, perfect. Great.
Okay. So okay. I stop. We are fine.
Okay.
Okay. Thank you.
So let's give me one moment in order to set up the... We are waiting for Mrs. Kroku. Okay. Είναι ο πυρετός τώρα των...
Ναι, γιατί στο συλλογάκι του βιντεάκι, γιατί θα βάλω εδώ το βιντεάκι.
Ό,τι προτιμάτε.
Είναι πιο...
Μισό λεπτάκι ώστε να στείλω ένα μήνυμα για να ξεκινήσουμε. Νομίζω, εντάξει, και τέταρτο ξεκινήσουμε.
Και τώρα εδώ έχουμε μάσκες και βλέπω να σε κάτι νοσήμα. Η φωνή είναι μεταξύ.
Ναι, την έχουμε δοκιμάσει. Εκεί. Δώστε μου παρακαλώ μισό λεπτάκι. With the Okay. So we are going to start in about 10 minutes. Okay. I will try to switch the camera view from here actually to the other camera. Έχω βάλει αυτή την κάμερα για να κοιτάει το τηλεσκόπιο βασικά. Στον Έστωρα ήσασταν... Okay, so we're about to begin in 10 minutes from now. We are already live on YouTube. Hello, Mrs. Kroku.
Good evening to everybody.
Good evening. Everyone who is going to present, I will make them co-hosts in order to help the process, okay, so that they can share their content. Okay, so, yes. Okay, now έχουμε συμμετοχή 2.500 άτομα στο event περίπου. Απλά να το βρουν, γιατί η δουλειά έγινε, δηλαδή η συνέντευξη ήταν εξαιρετική.
Δεν έχουν πει στο Zoom.
Από
notification έχουν πει στο Zoom η δική μας.
Έχει πει
Καλησπέρα σε όλους. Και με το όλους απευθύνομαι και στα δύο ημισφαίρια της Γης, αλλά πιο συγκεκριμένα στους κατοίκους της Ελλάδας και της Νοτιού Αφρικής, από όπου θα πραγματοποιηθεί σήμερα η παρατήρηση αυτού του μοναδικού φαινομένου της πλανητικής συνόδου, του Δία και του Κρόνου, των δύο γιγάντιων αυτών πλανητών του ηλιακού μας συστήματος, ένα γεγονός που συμβαίνει κάθε περίπου 400 χρόνια. Η εκδήλωση, που είναι υπό την αιγίδα του Γενικού Προξενείου της Ελλάδας στο Johannesburg, μεταδίδεται διαδικτυακά σε όλο το πλανήτη. Για να καταλαβαίνουν λοιπόν όλοι, επιτρέψτε μου να συνεχίσω στα αγγλικά. Good afternoon. I am proud to inaugurate this special event that happens only once in 400 years. We will witness today the great conjunction between the two giant gas planets of our solar system, Jupiter and Saturn, that will almost meet, shining virtually as one in the sky, as seen from the perspective of the Earth. The 2020 Great Conjunction of Jupiter and Saturn is the closest the two planets have been since 1623. And nearly 800 years had passed since this alignment occurred during the night sky, which means that the last time it was visible at night was during the High Middle Age in 1226. This is a one-in-a-lifetime astronomical event. I would like to thank all the participants that have contributed to make this transmission possible. First of all, I would like to extend all my gratitude and my thanks to Dr. Sophocles Sotiriou of the Ελληνογερμανική Αγωγή School for eagerly responding to my call for cooperation between the two countries, proposing this idea, and to all the persons involved at the school. Also, Professor Hamandaris of the Skinnacas Observatory in Crete for embracing this project and offering his cooperation from the start. From the Southern Hemisphere, I would like to thank the Boyden Observatory and the University of Free State for their readiness to engage to this initial cooperation with their Greek colleagues, mostly in the field of education. And personally, I would like to thank the rector of the University of Free State, Professor Francis William Peterson, and his colleague at the Boyden Observatory for hosting us there. A visit which, apart the opportunity that was given to us to observe directly celestial objects in the magnificent night sky of South Africa, eventually led to this cooperation. I also want to thank the Hellenic Federation of South Africa and the Hellenic community of Bloemfontein that helped organize the visit to the Boyden Observatory. And finally, I would like to thank the Saheti School for being part of this event and helping bring together the students of both countries. This event is under the auspices of the Consulate General of Greece in Johannesburg. It is part of our effort to bring closer the communities, the schools, and the scientists of Greece and South Africa. The starting point was my visit to the Boyden Observatory, the so-called Paras Observatory, as it was established by a Greek, Ioannis Paraskevopoulos, who in 1927 installed this telescope in South Africa. This is a fact that the South African astronomers working at Boyden have never forgotten. I will not say anything more about Paraskevopoulos, since I think there is a presentation dedicated to his work later on. I will just mention that not only was he a recognized astronomer, having a crater on the dark face of the moon named after him, as well as 2 comets and 1 asteroid, he was also considered a leader of the Hellenic community in Bloemfontein, a fact that shows us his enduring ties with Greece. As the gas giants of our solar planets are drawing closer together, we hope that this initiative will give the opportunity for the two countries to come closer together, sharing this event and also engage to a cooperation in the scientific and educational field. If we look up to the sky, we will realize that despite the distance of thousands of miles, the mechanics of our solar system is giving us today the same bright shows regardless our location. Today, under difficult circumstances of the pandemic, we would like to share an optimistic view with all of you, as today, sky's the limit. Enjoy the observation. Καλησπέρα σε όλους.
Mrs. Kroku, this is, we are giving the floor to you now. Mrs. Kroku comes from Ελληνογερμανική Αγωγή. And she will be welcoming you to our event. Mrs. Kroku, the floor is yours.
Thank you. Good evening to one and all, and a hearty welcome from Ελληνογερμανική Αγωγή in Greece. My name is Eleni Kroku, and it's truly a pleasure to be part of this one and only experience. I would like to welcome, in no particular order, Mr. Ioannis Pazandonakis, Consul General of Greece in Johannesburg, Professor Vasilis Karouliaris, Professor of the University of Crete and Director of Skinnakas Observatory, Mr. Warwick Taylor, Executive Headmaster at Saheti School, Professor Matthias Hoffmann from Boyden Observatory, Professor Peter Mankis, Professor of Astrophysics at the University of the Free State, Dr. Sophoklis Sotiriou, Director of the R&D Department at Ελληνογερμανική Αγωγή, Mr. Emmanuel Chaniotakis from the Observatory of Ελληνογερμανική Αγωγή, Mr. Giorgos Athanasopoulos from the Observatory of Ελληνογερμανική Αγωγή, Mrs. Helene Zvagedi from Boyden Observatory, Mr. Lucas Erasmus from Boyden Observatory, Mr. David van Jaarsveld from Boyden Observatory, and of course, a great welcome to our teachers and students from Saheti School and Ελληνογερμανική Αγωγή. An event such as tonight's isn't only the great conjunction of Jupiter and Saturn, but it is a conjunction of two schools that I have been blessed to be a part of and hold dearly in my heart, Saheti School and Ελληνογερμανική Αγωγή. And of course, a third conjunction of education and science. Three simultaneous conjunctions, all under one sky at one time. We are holding this online interactive event in the midst of a cataclysmic event, one that I believe will change history and is changing history in profound ways. Societal changes are occurring and are resulting in terms of how we learn and communicate, all due to technology. Distance is becoming smaller. People are getting closer. And how appropriate. Tonight's interactive, Tonight's interactive experience is just that, the meeting, the coming together of two planets. Coronavirus may have bound us at home, isolated us from social activity, but that will not stop professors, teachers, students, and mankind from meeting. Technology has not only enabled us to move forward, but it has enhanced the ability of conjunction. Bill Gates once said, "Never before in history has innovation offered promise of so much to so many in so short a time." And how true is this? We are homebound, limited in our physical conjunctions, yet we are all here, together, present and active to observe a once-in-a-lifetime phenomenon. Let us welcome the night, as it is a time to welcome what shines, the great conjunction of Saturn and Jupiter, the star of Jerusalem. Thank you.
Thank you very much, Ms. Kroku. Now I'm giving the floor to Mr. Warwick Taylor, Executive Headmaster of Saheti School.
Good evening, all. To those watching this live broadcast of the Great Conjunction of 2020, I'd like to thank Mr. Chatzimarkakis, the Consul General of Greece in Johannesburg, for including Saheti School in this program. I also thank Dr. Soteriou for his organization, which has made today possible. As with the Great Conjunction, where two bodies align and produce a greater light, joining two nations and schools across the globe enhance our experience and understanding. I trust that this conjunction is symbolic of future collaboration and alignment between our schools and our nations. The conjunction of Saturn and Jupiter, as we all know, is not a new observation, but has been recorded in history for thousands of years. There's a strong possibility that this same conjunction explains the Star of Bethlehem as recorded in the book of Matthew within the Bible. We know that the conjunction happened 3 times in 7 BC, in May, October, and December, with the constellation of Pisces in the background. Astronomers or magi at the time interpreted Jupiter as the planet of kings and Pisces as symbolic of Israel. Therefore, the interpretation of a king born to Israel was not unlikely at the time. Whether or not the Star of Bethlehem was this great conjunction that we're going to be viewing tonight, or a comet of 5 BC, astronomy has helped date significant moments in history. I trust that we all take a moment tonight to reflect on how majestic our universe is, to look in awe upon our creation, and the lessons to be learned from the sky that reveals billions of years of information to the educated mind. In closing, a quote from Albert Einstein: "Look deep into nature, and then you'll understand everything better." Σας ευχαριστώ.
Thank you very much, Mr. Taylor. We thank you for being here with us. And now let me give the floor to Mr. Vasilis Harmandaris, Professor of University of Crete and Director of the Skinakas Observatory. Professor Harmandaris, the floor is yours.
Thank you. I would like to thank you for the opportunity given to us to participate in this exciting event. First of all, as everybody said, it's a unique opportunity to have scientists and students for 2 nations in the northern and the southern hemisphere to join and explore the night sky in such a unique situation. There are many people to be thanked, but I think the person behind all this was Dr. Soteriou, who was the person who actually organized everything, and of course the Consul General, Mr. Chatzimarkakis from South Africa, who brought us all together. I think later down in the program I will have some time to make a small presentation about the usage of these planets and how they inspired people to actually do some basic calculations. But I would like to stress, as other people have mentioned already, the fact that collaboration between nations has been proven instrumental in actually the development of civilizations. Having the opportunity to actually live in the island of Crete, where the island has profited through the millennia from cultures and civilizations from the Phoenicians, the Egyptians, and the people of the ancient Greek city-states for the development of the Minoan civilization. It is clear to me that if we continue along this path, we only have to gain in making our lives better through applied science and also actually understanding each other better. So I do look forward to this event, and hopefully the skies will be clear either north or in the south, and we'll be able to experience this event, all of us, through our computers. Thank you.
Thank you very much, Professor Harmandaris. So We are about to start now the next part of our event, in which we will be discussing about the Great Conjunction, and we will be trying to see how the phenomenon is viewed from Greece. Unfortunately, right at this very moment, the sky here in Greece is not helping us. However, we will try our best, first of all, to convey the message and to understand together the physics behind the phenomenon, and to show you what is expected to be observed. So allow me please to share my screen now. Okay. So first of all, my name is Emmanuel Haniotakis, and together with Mr. Athanasopoulos and Dr. Sotirio, we represent the Ελληνογερμανική Αγωγή School Observatory. So let me first of all say a couple of words about what you are about to observe. So from the Northern Hemisphere, okay, I will show you the video a bit later, what is expected to see from a telescope with moderate magnification is an image like the following. You will see Jupiter on the bottom right, and you will see Saturn on the topmost left, okay, and the distance actually that they have, the angular separation as we call them, is the smallest observable in our times. We will come back to that a bit later. First of all, allow me to give you to tell a few words about the Ελληνογερμανική Αγωγή School Observatory. So, the observatory of Ελληνογερμανική Αγωγή was installed in 2007, houses a 16 inches f10 40 centimeter Middelix 200 arts mid-Cassegrain telescope, okay, and also smaller telescopes. The telescope is housed in a 12-meter high and 6.3 diameter. Though its unique location within the premise of a school allows teachers and students to be able to engage actively with scientific research in observational astronomy. So the observatory is dedicated in education and outreach purposes mainly, but is also participated in research, both in observational astronomy and in educational research relevant to astronomy. So I will give a very, very brief introduction to the protagonists, let's say, today, Jupiter and Saturn, and they will be discussed in detail a bit later. So, Jupiter is a gas giant, is a gaseous planet, the largest and most massive planet of our solar system. The period of revolution around the Sun, meaning years, so to say, is 11.86 years, whereas the average distance of the Sun is 5.1 astronomical units. Just to help you with that, the distance, the average distance between the Sun and the Earth is 1 astronomical unit, so 5 times. Now, the apparent magnitude now is minus 2.94 minus 1.56, which is quite bright, and they can be very clearly observed with a human eye. The angular diameter Saturn now is once again a gas giant, the largest planet from Earth, discovered by the amazing human eye. It has a characteristic ring cloud, and the period of revolution around the Sun is 39 years. The average distance of the Sun is 9.5 years. Less than 7 between Jupiter and Sun. The apparent magnitude to be lower is when this distance can be related to the magnitude of Okay, so if you tried to, yes, I will try to speak louder. So if you would like to put everything on paper somehow, you would see that the sun here is in the middle, the Earth is the trajectory of the Earth is this one, this is Jupiter, and this is Saturn. And so we have actually taken this and see a bird's eye view of the phenomenon of the conjunction, in which we can see that the positions of the Earth, Jupiter, and Saturn are almost aligned here in the Great Conjunction of 2020. If you go to a clear night sky and observe, you will see in the northern hemisphere that Jupiter and Saturn are observed as follows with the naked eye. You can see here why Jupiter, we call that it has, it is brighter and Saturn is dimmer, okay? And now it's a good moment to introduce the Great Conjunction. So what I want you to do is actually to imagine that all planets are somehow running in their own racetrack, okay? They have their own velocities, okay? And we can take into account that the Earth completes one full orbit in 1 year. Jupiter, which is 5 times further from the Sun than the Earth, takes something less than 12 years, and Saturn about 29 years. So at some points in time, the 3 planets' positions are aligned, and this is what we call a conjunction. This happens almost every 20 years, and the timing of the conjunctions depends on the relative positions and velocities of the 3 planets. This happens in general almost every 20 years. However, every almost 400 years, the alignment of the 3 heavenly bodies is such that the 2 gas giants observed from the Earth's vantage point are 0.1 degrees apart and cannot be resolved by the human eye. So this is actually the observational characteristic that has made us call it Great Conjunction. It has happened again in 1623, and it has been actually referred upon by Johannes Kepler in his book, De Stella Nova. And the next one, luckily for the youngest of us, will take place in 2080. So I would like now to go to a simulation in order to show you how the event is happening. So what you see here, again, is the Great Conjunction as it is observed from space. So I will be going now to my browser, and I will try to show you around the effect. So what do we have here? This is from Open NASA website, and what we have here is a simulation to scale of our solar system and the trajectories of the planets. So what we can do here is that we can put a starting date, and we can start now observing the progression of the revolution of the planets around the Sun. So I will start, let's say, in August. You will see that it goes rather fast. I want you to have a good look, because the bluish one, the bluish trajectory, is our Earth. This one, the orange one, let's say, represents Jupiter. And beyond that, the yellowish one, let's say, represents Saturn. Okay, so we start from October the 8th, and we start playing to see what happens. You see that the time progresses here, and you will see that the planets are moving, some of them much faster, some of them much slower. And here we are now, we are near the 6th of December, which was about 15 days ago. And I would like to prompt you to have a good look at what happened then. You will see Saturn and Jupiter, their positions and if you draw a straight line from there to intersect the blue trajectory, you will see that the three planets are almost aligned. I will show you the same thing from the point of view of the Earth in a bit. Now, we are at the 22nd. I lost it for a day. You will see now, if you draw this imaginary line, that the three planets are indeed aligned. And if I go back and see it from the point of view of the Earth, and I ask to observe, let's say, Jupiter, okay, and I will go back a bit. Let's see what happens. You see Jupiter approaching Saturn. What you observe here is that the two planets are coming closer. Are they really coming closer? Well, actually no, because as we said before, Jupiter has a distance from the Sun, which is of the order of 5 astronomical units, whereas Saturn has twice that distance. Therefore, from our vantage point, they are getting closer. And we are almost there. You see, this separation is measured in degrees or radians in angular units. And here we are today, where the two of these two planets are almost, let's say, on top of each other as we observe them from the Earth's vantage point. So this is what we call the Great Conjunction. If I go back now, I would like to show you, this comes from the CCNY planetarium. You observe the phenomenon as you can see it with your naked eye. So as time goes by, the two objects, Jupiter and Saturn, as you observe them here, are coming closer, and at the 21st, today, actually, they are on the Great Conjunction. So here we have a nice exercise, let's say a sort of game one could play, because we are lucky to have with us our South African colleagues, and we would like to investigate what do we expect to observe in the South and the North hemispheres. So we are somewhere here in Pallini, Greece, and here you observe what the phenomenon looks like as time goes by. So you see that in September the 21st, the angular separation of the two bodies was of the order of 7.5 degrees, and here the separation started decreasing. Now, in order to understand the scale of the phenomenon, imagine that the moon, the full moon, has a diameter of 0.5 degrees. So this means that in November 21, we had about 6 moons, more or less, that could get inside this space as we observe them from the vantage point of the Earth. But this decreases. And now, on December 21st, we observe the phenomenon having the separation of the two gas giants being the 1/5 of the lunar diameter. If you go back and see what happens in South Africa, where our colleagues are situated, you will see that the phenomenon is similar, of course, but we have a small difference because we are seeing from different latitudes. You will see here that when in the northern hemisphere, Jupiter, as observed, was in the bottom right, Saturn was in the top left. And in the southern hemisphere, it goes reversely, let's say. Okay, so we have Jupiter on the bottom left and Saturn on the topmost right. So here you will see a live, the live view we had in December 19, 2020. And you see how the effect was observed in Boyden and South Africa, Boyden Observatory, and how it was observed in Ελληνογερμανική Αγωγή Observatory in Pallini, Greece. Okay, so you see this is Jupiter, this is Saturn in Greece, this is Jupiter, this is Saturn in South Africa. Now, we have, let's say, the conjunctions Hunter's cookbook. So this is an event in progress. This is the relative position, let's say, of the two planets changes with respect to time, and at some point they get to their nearest approach. Okay. So in Greece, the effect is observable from sunset until about 7 o'clock in the afternoon, where it is below the horizon, of course, weather permitting this. And it can be seen with naked eye, binoculars, or a telescope. Now, if you want to observe the Great Conjunction with a telescope, you need to take into account some further effects. So first of all, if you try to observe something with your telescope that is more or less 10 degrees or less above the horizon, it will be very difficult because we have light pollution, especially if we are in the city, and we have seeing, let's say, the atmospheric turbulence that creates these blurry images that we have. So, in fact, the observational window that we have in Greece is of the order of 40 or 45 minutes. So what do you need in order to observe the conjunction? You need you need good weather, first of all, and clear skies. You need a telescope with moderate magnification in order to include both planets in its field of view. Again, we said it's 0.1 degrees angular separation, and we have some more characteristics here that are not important right now. Of course, if you want to couple a camera with that, you need to have a larger sensor in order to cover the telescope's angular field of view. So, allow me to show you a video in order to see the live view of the phenomenon. This came a few days ago from the Pallini, Ελληνογερμανική αγωγή, in Pallini, Greece. This is Jupiter, again. This is Saturn. And here you can understand the fact that this is Jupiter because we have the satellites here. Again, this is a couple of days ago, so the relative position of the two has decreased right now, and the position of the satellites is a bit altered as well. And I would like to draw your attention to the fact that since it is so low in the horizon, it is very difficult to get a clear image. You see, it is blurry, it's moving. This is atmospheric effects. Okay. If there is any question, I would happily answer them for a moment in order to proceed to the next part of our presentation. If the students who are with us would like to ask something, or anyone? Okay. So, what is important to discuss, unfortunately, I will try actually to show you a bit the sky here. I will put this, I don't know if you can see Mr. Athanasopoulos' screen. I will try to, I will stop the sharing for a moment, and I will show you. You can see here the view from Pallini. So right now it is night, okay? And you can see actually that the point where the conjunction is, it is full of clouds. So unfortunately, the weather is not that helpful for us right now. However, let's go back and share the screen. because I would like to show you a couple of things more. So we showed the gas giants as they are observed, let's say, from our vantage point here. Okay, and you see two actually very small dots with lots of difficulty to produce, let's say, a clear and high resolution image. So how do we do that? And this is the next part of our presentation, which discusses the photo shooting of the gas giants. So what you saw before was the live view of these bodies. So in order to do a proper imaging, we need to do a specific procedure. And what is this procedure about? Well, there are many ways, but the standard procedure that we follow requires the following equipment. Our telescope, in our case, a 16-inch Schmidt-Cassegrain telescope. Okay. We need a planetary camera, you can see it here, okay, with which what we actually do is called lucky imaging. And we also, and we will discuss about that later, and we also need some software in order to be able to process the images that we will get from our camera. So let's take it step by step. Okay, so I will try to show you now the image of Okay, so what you see here actually is the live view of Saturn a few days ago, and what you see is actually that this is very blurry. You see that we have produced a video. Why do we do that? What is a video actually? If you think about it, a video is a series of snapshots, all joined, let's say, together. So what we do in lucky imaging, you will observe, first of all, that some of the pictures are more blurred and some of them are more clear. Okay. So the point is that in order to be able to do image processing here, we need to take many underexposed, as we call them, images, okay, which means that the exposure time is of the order of some tenths of milliseconds, and we take this video for about 1 minute. So what do we do with that? What do we do with that is the process of stacking afterwards. So in order to stack, we will be using a software called AutoStacker. Okay. And my colleague, Mr. Athanasopoulos, will be handling the computer from now, and I will be explaining, so to say, the procedure. So what do we do with that? What we do is actually, we take this video and we try, let's say, to isolate the most high quality images of that. This is the process that we will follow right now. You will see that this histogram here displays the quality, and let's say the 100% quality is on the right, and on the left is the highest quality, let's say, images. So if we select here, you see how the quality drops with respect to the images that we see. And if you go here, you have effectively selected about 50% of the images that you use. Okay, so this is about 1,500 images that have been selected out of the about 3,000 that have been captured. So it's about 50% here. Okay. So what we do here is that we create points in the full picture, and we are selecting, let's say, the highest quality images. You will see, yes. And then the process is stacking. So what is stacking actually? Stacking is something like averaging the photos that you see. Because what do we mean averaging? It means that you have some noise, some random noise coming from the camera, but you have also the turbulence. However, these patterns, let's say, illuminate some of the pixels that we have, but they do it in a random fashion. So by stacking, we are averaging the images. Therefore, we are enhancing the so-called signal-to-noise ratio. Therefore, noise is suppressed, whereas the signal is enhanced. So in this framework, the next part of the process is that after the stacking has been done, we will need to be able to control, let's say, the image's characteristics with a series of, let's say, using some photo processing software. And an example of such a software is Registax. So here we will try to show you immediately the result that we have, okay, about Saturn. So the process that you will see that we did actually took us from the live video, and after processing, correcting for the contrast and other characteristics, this is the final output that we get in imaging Saturn. Similarly, I will show you the live view of Jupiter. Yes, here we are. Here you see the live view of Jupiter from our 40-centimeter, 16-inch telescope. You see again that we have this turbulence, and this is what our camera observes. Underexposure is essential here. Why? Because the exposure time is lower than the characteristic time of the atmospheric turbulence, the impact of atmospheric turbulence in our image. So I'm coming back, and I would like to show you Saturn before and after processing. You can see it here, and you can see quite clearly the effects. Okay, and we observe also Jupiter before and after the processing. Okay, so finally, allow me to come back again and show you a little bit the conjunction as it is observed from Ελληνογερμανική αγωγή. It was observed a few days ago. And in the meantime, I will be happy to receive any questions that you may have. I see that we have some questions in the chat, possibly. No, it is about the sound. Okay. So, are there any questions? Okay. If not, I think we are quite a bit earlier on schedule. I would like to thank you and wish to everyone Merry Christmas and a Happy New Year. And I would like to pass the baton to Professor Harmandaris, who will be discussing with us some very beautiful physics regarding Jupiter.
Thank you, Manoli. what I would like to do now is I would like to share my screen and show you a presentation that I prepared. I think, I presume you are able to see it now, right?
Yes, yes, thank you.
Maybe I should close my camera to make it a bit simpler. So the idea of this presentation is to actually demonstrate how using Jupiter and Saturn in a sense, one could do some fundamental physics. And people several hundred years ago and even in the past were actually thought about it. And there are two experiments here I'll be mentioning. One is how one could use the satellites of Jupiter as a cosmic clock, and also how one could measure the speed of light using those satellites. And one should remember, I presume that most people in the audience are aware of this. What is astronomy, right? Astronomy is an effort to actually touch and understand the universe that surrounds us. This is a beautiful drawing from the 19th century. It was shown by a French astronomer and populist writer Flammarion, where it shows the effort of humans to actually touch the heavens, look up in the sky and try to understand why the planets move and wander around the stars, why the stars rise and set, and how peculiar objects appear and disappear as novae or supernovae, or objects which have hairy tails, and calling them comets. And the effort, the two problems is the longitude problem and the speed of light. It's interesting to put things into perspective and actually realize actually what, when we talk about the universe, what are the places of the universe that humans have set their foot. And there are only two places. It's our own planet and the moon, which you can see it on the side. All other knowledge that humans have obtained, they retrieve this information by studying the light of celestial bodies, basically. And here you can see the Earth and the Moon. If you would put them side by side, the Moon is probably a quarter in diameter. And if you try to do some quick calculations, you will actually see that in the order of 100 billion people have lived on planet Earth. However, only 12 astronauts, all males, have actually made it to the moon. So if we have ambitious young female students, this is a first that they could achieve if they put their mind into it. And the reason why there are only 12 astronauts that have visited the moon so far, it's because if we put things into perspective, and you actually have the Earth and the moon to scale, and you put also to scale their distance, you will actually see that the moon is not as close as we think. The distance to the moon is nearly 30 times the diameter of the Earth. It took 3 days for the astronauts to make it there with Apollo mission. But for the light, it takes a little over a second, 1.3 seconds actually, to travel that distance, right? So if you were to see the moon tonight, you look at the moon the way it was a bit over a second ago. And if you were actually to think how big this distance is and to put it again into perspective with something that we are more familiar about is if you were to go with 160 kilometers per hour, if you were a Formula One driver or possibly an average person driving in the German Autobahn, it would take you 100 days at nights to cover that distance between the Earth and the moon if we were able to build a bridge which would connect the two celestial bodies. So the distance is astronomical, and it's good to keep that in mind because we will see it further down. So, and also Manolis already pointed this out, but if you were to put again things into perspective and you were to see the sun and the planets of our solar system, which are we're discussing tonight, the Earth is very small compared to the sun. You can see it as a dot in this plot. It's 100 times smaller in radius than the sun, a bit over 100 times. It would fit, you could fit the whole sun with 1 million of balls the size of the Earth if you were to do it, right? And if you were to compare the Earth with the two giants of our solar system, Jupiter and Saturn, you could actually see that the Earth is in the order of 10 times smaller in radius, and again 1,000 times smaller in volume than what Jupiter is. So we are very small compared to the other objects in our solar system. And again, as you saw by NASA here, you can also see the orbits of the planets as they go around the sun, again into scale. And you can see the sun at the center and Mercury, Venus, and Earth wandering around. The Earth is over here. The other orbit is the orbit of Mars. You have the asteroid belt, and then Jupiter and Saturn further out. And as it was mentioned, if you say that the distance between the Earth and the Sun is unity, 1, Jupiter is a bit over 5 times further out, and Saturn is 9.5 times further out from the Sun than Earth is. Now, Jupiter was actually observed by naked eye through millennia by humans, right? But nearly 400 years ago, a new technology was developed, the telescope, by Dutch sailmen. And a scientist and genius of the epoch, Galileo Galilei, took this new technology, the telescope, and looked at the heavens with that telescope, right? He made several discoveries. Some of them actually made his life a bit more difficult. But one of the major discoveries that he made was actually he observed Jupiter, which was a known object, right? But he identified 4 bright spots wandering around Jupiter. And here you can see on the left some of the drawings of Galileo at the time. And you can see Jupiter as a bright, as a circle. And the 4 spots here observed at different days are the 4 the Galilean moons, as we say, the brightest and largest moon of Jupiter. In this table here, what we have is that we have the names of the 4 moons, Io, Europa, Ganymede, and Callisto. And here you can see the period in days. Io, which is the closest one, has a period of 45 hours or so, 1.7 something days. Europa takes longer, 3.5 days. Ganymede, a bit over a week. Almost 2 weeks, a bit more for Callisto, right? And as one would expect, the farther out you are, the longest it takes for the satellite of Jupiter to go around, right? Just to put it in perspective, Io is a bit further from the center of Jupiter than the moon is from the Earth, right? It's something like 20% further. Soon after Galileo made these observations, it was clear to him that he could actually propose to use those to measure the longitude anywhere on Earth. And I'll just insert here this picture to actually see, again in perspective, Jupiter on the left, and the 4 Galilean satellites also put into scale, right? You can actually see they are fairly nearby Jupiter, right, if you were to put them into scale. Now, the longitude problem is it's a very interesting problem, and it's a major applied science problem. And the problem is basically how one can locate the position of a ship who is sailing in the seas, right? That was a major problem since basically humans wanted to explore our planet. And when in the Middle Ages, sailors moved from continental Europe out west to rediscover Indies, the West Indies, and hit upon North America at the time. We all know that it is easy to determine the latitude, which is, as we know, how far up north from the equator of the Earth we are located, while longitude, as we know nowadays, is we have defined the prime meridian, the one passing through Greenwich just outside London, and you measure the distance, the angular distance on this sphere west or east from this meridian. Determining latitude is easy. Most of us have probably done it. What you need to do is you are here, you can see a schematic of the celestial sphere as we know. This is the average person. Zenith is up north, above the sky, excuse me, just overhead. The north celestial pole is towards the north. The Earth is rotating. And if you are to identify the northern star, if you live in the northern hemisphere, which is Polaris, and you measure the distance, excuse me, the azimuth, the altitude of the star above the horizon, how high above the horizon this star is, the northern star, you can actually estimate your latitude. This is the exact angle. If you are on the southern hemisphere, you can do the same thing using the Southern Cross. To estimate, though, the longitude is much harder, and as we will see later on, because and it was imperative to do that because up until the Middle Ages, the way sailors, ships who were moving on the Earth were basically going by the seashore and then moving along lines of constant latitude. However, this was a problem because pirates also knew these routes, and there were great disasters that took place, and it was a very important problem for the economy of both Spain and Great Britain at the time that were doing a lot of trade between the New World in the Caribbean and North America and Europe, right? So a price was set to actually determine the longitude. And this was, a committee was established in Great Britain in 1714 by Queen Anne. And the prize was financially extremely high. It was, in today's value, it's worth 3.1 million euros if one was able to propose a method by which an average sailor on a ship could actually estimate its longitude, the position, with an accuracy of 66 kilometers. Right? That was a lofty goal. Right? Now, the idea on how to do that was effectively proposed by Galileo, even though it was not applied directly by him, as well as Cassini in Paris Observatory. And the idea was based on the fact that people could measure time on ships. They had clocks which were sufficiently good to measure accurately time just for a day. They could measure time accurately for a bit less than 24 hours. And every day at noon, they would know that the sun was highest up on the sky. So they would know that it was midday and keep on going in that manner. But so the idea was that they could create tables with the location of the 4 moons of Jupiter as they were seen at midnight from a given place on Earth. For simplicity, let's say that this was Greenwich, right? So you say that at midnight from Greenwich, seen from Greenwich, Io is at so much to the left of Jupiter, so many arc minutes, Europa from the other side, and so on and so forth. So you actually make those tables which specify the location of those satellites at a given time. Then one from a ship could actually measure the time of midnight. That was something that could be done, and look at those moons. measure the positions of those moons with respect to Jupiter, and then go into these tables that they had them on the ship, and actually estimate the time difference between the measurement made on the ship and the measurement that was made on Earth, or the predictive position of the satellites as they were to be seen from Earth, right? Because the periods are constant, so you could actually make those tables. So measuring this difference in time is directly translated to longitude by multiplying every hour by 15 degrees, because we know that the circumference is 360 degrees and it takes us 24 hours to actually go around. So this was the method that was applied, that was proposed. Unfortunately, it was not established because on ships, because it was fairly difficult to actually perform this type of astronomical observations. It would take a trained person to actually observe from a moving platform Jupiter and its satellites, and actually make measurements of the angular distance between the satellites of Jupiter and the planet itself. The actual solution was proposed to this problem by John Harrison, who was able to build a very accurate chronometer. You can actually see the chronometer here in this picture on the bottom left. And he was finally awarded the prize, not the full amount, in 1773. He was almost 80 years old when he was able to get that prize. And it is a fascinating story about how this whole endeavor took place. And there is a beautiful book for those who are interested. It's an old book, almost 20 years old, by Dava Sobel, which describes this effort to measure longitude on the Earth using either astronomical methods, such as the one proposed by Galileo and Cassini using Jupiter's moon, or a clock and a chronometer, actually, as the one by Harrison. So the other problem, it is related to actually how one can measure the speed of light. This is an interesting problem, and the first attempts on this were proposed by Isaac Beckman and Galileo. That dates back almost 400 years ago, as you can see. And the idea of both men was simple. Like, the idea is that you have a person, you can see the figure here on the left, and you have another person waiting at some distance away. The first person needs to have a clock and also has a lantern. The first person lights the lantern or makes it appear behind an obscuration. Light travels from the first person to the second person. As soon as the second person observes the light, she lights or makes appear her own lantern, and the light moves from the second lantern back to the first person, who at that time actually controls how much time it took for this whole event to take place. So if you were to know the distance between the two observers, and twice the distance was actually the distance traveled by the light beam, and if you knew how much time it took for the light beam to cover that distance, then you divide the two and you get the speed of light. Very simple, right? So this was what was proposed, but no result could actually be obtained. And the reason why no result could be obtained was because of the fact that light moves very, very fast. So if you are on one mountaintop and the other person is on another mountaintop and they have sufficiently bright lanterns, then if the distance is too small for the time it takes light to actually cover it, and the reactions of the people who were just not substantially longer than the actual time travel of light. So this experiment, though correct in principle, could not be provide an answer to measuring the speed of light. However, there was another Danish astronomer, Ole Romer, who was working at Paris Observatory, had another idea. And the idea was actually what one could do was actually to use Jupiter and its moons to actually measure the speed of light. And here on the right, what you have is you have the sun, and you have in a drawing the orbit of the Earth around the sun. And on top you have Jupiter marked with B. These are from Romer's drawings. And you have Io, who is rotating around Jupiter. As we said, a bit over 1.7 days or so, that's the period, right? So what Romer observed was that the time that was elapsing between the eclipses of Io by Jupiter was not constant. Because when you are from the right side of the Earth, right side of the sun, as the Earth revolves around the sun, say when you are at point F or G, Io would actually, as it goes around Jupiter, it would enter the shadow of Jupiter, so it would disappear. And then it would reappear from the other side at point D, even though this was not visible from the Earth, right? And this would happen again and again and again. And Romer observed that when the Earth was moving towards Jupiter, when it was going from F to G, it appeared that the eclipses were shorter by 3.5 minutes than what one would expect. And on the other hand, when the Earth was from the other side of the sun, and it was moving, say, from point L to K, and Io was reappearing behind the orbit of, behind the shadow of Jupiter, the actual timing between the eclipses was longer by 3.5 minutes. So since at the time it was already established what the distances between the Earth and the Sun and the Jupiter and the Sun were, the only explanation to this phenomenon, assuming that the orbit of the period of the orbit of Io is constant, is that the speed of light is actually finite. And if one makes some calculations, and Romer actually did it, one can estimate the speed of light, and it was found that it was 215,000 kilometers per second, which is only 28% of the actual correct value that we know today. So if you think about it, it is fairly impressive how using very simple instruments which were much less accurate than the ones we will be using today, or the ones that are available in a school like Germaniki, for example, motivated and bright individuals were able to understand the heavens and estimate fundamental physical constants such as the speed of light. And here you can actually see some of the notes of Romer, and his handwriting is not impressive, as you can see, but it's interesting to actually see that he started measurements from 1673 all the way to 1677. You have all his notes, different February, March, and so on, all the dates, etc. So it is, and all this is recorded, and some of it is available in the archives at Paris Observatory. So closing, what I would like to bring into our attention is sort of like this effort to study and understand the eternal sky is something that has been taking place from thousands of years, right? Our ancestors, some of them, and people all over the world, the ones in Crete actually, in Greece, what they did is that they looked up in the sky, and they were amazed by the beauty of the night sky, and they actually placed their gods on the sky, and made stories about their mythology, right? So if you are Greek, you can actually identify Cephids and Cassiopeia, who had a daughter which was called Andromeda, and they had to sacrifice their daughter, and Perseus came with the flying horse Pegasus to actually save the daughter of the king. But in parallel, what people did and scientists started doing nearly 3,000 or 4,000 years ago, they were actually observing carefully, and they were trying to measure accurate measurements, as accurate as the technology of the epoch allowed. And reducing the uncertainty in the measurements will actually improve our knowledge about the phenomena observed. And they actually tried to explain those phenomena using logic and theories rather than faith. And this is very important for the development of science. And this quest actually continues even today. And we have this type of tools. We are very fortunate. And there are observatories across the globe. One is down south at Boyden. Another one is in Crete, which is Kinakas. And we are all looking forward to be using them and try to understand the world around us. Thank you very much.
Thank you very much, Professor Harmandaris, for this great presentation. So, do we have any questions? We would like to encourage our students, if they have any questions that they have, please don't hesitate to ask them.
I think I saw some students. I don't know if there are questions in the chat, maybe.
No, as of now, there are not. Okay. So, Professor Harmandaris, thank you very, very much.
You are very welcome. Thank you for organizing this. It was exceptional.
Thank you. So, I think that we can wait for a few minutes before we proceed to our Southern African colleagues who will introduce us to the sky of the Southern Hemisphere. Lucas, can you hear us? Patricia?
Hello, yes, we can hear you. Can you hear us?
Yes. Thank you very much. We are. Yes, please, Lucas. Yes.
Yes. Can we start?
Yes. Okay. So we are a bit earlier on our schedule. So the floor is yours. If you would like to give some intro.
Okay. Thank you very much to our Greek colleagues. Welcome to everybody to South Africa. We are currently here at Boyden Observatory. It's about 26 kilometers to the east of Bloemfontein. And this facility has a lot of history associated with it, and especially also concerning Greece, because the first director of the Boyden Observatory was Prof. Here is a plaque which we placed for him, which gives a bit of his history concerned with this observatory. And later on, you're going to hear in the talk of Mr. David van Jaarsveld, where he's going to go into depth about the history of the Boyden Observatory. And if you want to walk with me, we can go to the library that we have here at the Boyden Observatory. Now, this library was established by Harvard University in America originally. As you can see here, we have a lot of books from the Harvard Library. And also we have some historical equipment that we are currently sorting out and getting operational again for a museum exhibit. And if we walk around the desk and we look outside the window, We can see the rest of the Boyden Observatory here in the background. You can see also, unfortunately, but yeah, there to the left, we have our 13-inch Alban Clark telescope, which is mostly used for public engagement and outreach. And then there in the distance, you can see the 60-inch Boyden Observatory telescope. This is mostly used for astrophysics research. Now, as I said, unfortunately, we're currently experiencing some cloudy weather, and that's going to make things a bit difficult when we are observing the conjunction. But we are in contact with one of our colleagues in Centurion to the north of South Africa to hopefully provide us with video imagery of the conjunction later on when the sun has set. Also, you can see it's quite light outside currently, in contrast to Greece. And this is due to it being the longest day currently in South Africa. It's the 21st of December, and it's the longest day and the shortest night in South Africa, while you're experiencing the exact opposite there in Greece. So yeah, if you can just hand the camera here to me, then I can just give us a quick introduction to the person that's going to welcome on the South African part today. This is Prof. Marty Hoffmann. He's a South African physicist, and he started working at the Department of Physics at the University of the Free State in 1985 and obtained his PhD degree in theoretical solid-state physics in 1998 at the University of South Africa. Prof. Hoffmann is a makes regular contributions to broadcast and print media regarding astronomy and space news. He's also a regular guest on the popular radio program here, which is broadcast across our national public radio service. And Prof. Hoffmann is also a lecturer at the Department of Physics at the University of the Free State and also the director of the Naval Hill Planetarium. Prof. Hoffmann, the floor is yours.
Okay, thank you, Lucas. Let's just firstly confirm that everyone can hear me clearly.
Yes, we can hear Prof. clearly on the stream.
Excellent. Okay, it is a great privilege to welcome our wide online audience. I can mention, of course, Mr. Ioannis Chatsantounakis, the Consul General of Greece in Johannesburg. We had such a pleasant meeting with him, his wife, and members of the Hellenic communities in South Africa, and in particular in Bloemfontein. He took the initiative to connect us with our astronomical and educational colleagues there in Greece. Then we already had the privilege during preparations to have a view of the beautiful observatory there at the school, the Eleonogermaniki Agogi. You know, we have a bit of a trouble with the pronunciation. Mr. Eleni, Mr. Warwick Taylor, the executive headmaster, and then the director of the Skinalkas Observatory, Professor Vasilis Chamandaris, with his fantastic presentation. Also Manolis, who took made so many other arrangements, also for a fantastic presentation. I can imagine that I can imagine that Hipparchus and all those famous Greek astronomers and scientists would be very proud. And it's great to celebrate. I hear more voices coming in, but I hope you can still hear me. Okay, then on the South African side, okay, of course, also the learners there in Greece that is participating. You are actually the primary reason why the astronomers go through so much effort to share this fantastic experience of this great occultation with as many people as possible, and in particular, young people. On the South African side, we have also a special group of learners arranged by our colleague at the planetarium, Mariette Erwier. It is Free State physical science learners who take part in the ICT laboratory program at the University of the Free State. They have an intensive education program focusing on physical science and astronomy. And Mariette, as a staff member of that program, is making a substantial contribution. Then also here on the South African side, our own astronomy public, many of them that we know through our radio programs, through our Facebook program of Boyden Observatory and the Naval Hill Planetarium, my colleagues and co-presenters at the Naval Hill Planetarium, and then a very special and small group of people that from the Astronomical Society of Southern Africa. They're at the Boyden Observatory doing their best to dodge the clouds. That's from where Lucas just addressed you. That is Professor Tinus van der Merwe, Mr. Piet Leroux, and Quentin Kaplan, and as postgraduate astronomy students. We have my astronomy historian colleague, David van Jaarsveld here, Patricia Lamouse from the University of the Free State Advancement Office. We have other dignitaries of the university, and as you have heard, that our Vice-Chancellor, Professor Peterson, who attended the event at Boyden Observatory with the Greek community, he will also be sharing in this online event. So with that word of welcome, I give back to Lucas to guide us further along the program.
Thank you very much, Prof. Hoffmann. It's my pleasure now to introduce our first speaker for this evening from the University of the Free State side. This is Mr. David van Jaarsveld from the Department of Physics. He's a lecturer for natural agricultural science and also service learning. And he's also the curator. Can you please just mute?
Okay, now share the PowerPoint.
Okay. He's also, Mr. van Jaarsveld is also the curator of the Boyden Observatory Museum. He's also a well-known ambassador for Southern Africa astronomical heritage. Other than astronomical history, his passion is science communication. He makes a substantial contribution to astronomy awareness amongst the public and school groups as presenter of educational programs at Boyden Observatory. The floor is yours, Mr. van Jaarsveld. Please, Mr. van Jaarsveld, we haven't yet heard anything of you of the live stream. We are seeing a screen being shared. If you can just test the audio levels. Thank you very much.
Can you hear me,
yes, we
Lucas?
can hear you. Yeah, we can hear you now loudly and clearly. Thank you.
Okay, thank you. Let me just get the slideshow here. All right, thank you all for attending this cloudy night. Are we on the first screen now? Am I ready?
Yes, we are not seeing the screen share currently. We are seeing Mr. Piet Leroux, but we are not seeing the screen share.
Okay, just a minute.
No problem.
Ja, maar dat zien het niet.
Ek was gaan share screen toe.
Mr. van Jaarsveld, can you hear us? We are not hearing you currently.
Yes, I can hear you, but we have a little problem here with the share screen. But we are working on it. Okay.
De ander mense hoor ons, dis hulle probleem.
I can hear but I can't see.
Okay.
Waar is die hele flippend venster nou?
Dis nie meer tof. Dis nie meer tof. Dis nie.
Nog nie. Is hy?
Okay, sorry for the inconvenience. We are just waiting for our colleagues to, yes, there we have the live feed. Thank you very much. The floor is yours, Mr. van Jaarsveld.
Okay, sorry for this little delay. I think it's because of the cloudy weather we have. Then we're all under the cloud. Paschalopoulos was born in the year 1889, and incidentally, that's the same year that they built the Southern Station in Arequipa, Harvard. That year he was born, and there's a short synopsis of his life till his death in 1951. Here he is in the library of the station at Arequipa in Peru. And this is where he was born. Now, I'm not sure about the pronunciation, but it's Piraeus, maybe the Greek guys will correct me on this, but this is where Paschalopoulos was born in 1889. And I wonder why he ever will leave a place like that to come here. But anyway, we are glad that he did. He received his degree of Doctor of Science from the University of Athens in 1910. And he spent many years as a laboratory assistant, and he had King George II of Greece, the future King George II of Greece, as one of his students. Now his studies was interrupted by 9 years of military service, the poor fellow. It was the Balkan Wars, and when he thought that was all over, it was the First World War. He took part in 13 battles, and he got a medal for each one of them. So I don't know if the 13 was a lucky or unlucky number for him, but he definitely did his duty for his country in 9 years of war. I don't know, I don't think any astronomer can say that in the history. Then the Greece government sent him to Yerkes Observatory to investigate the establishment of a big telescope for Greece. That did not happen because the wars, of course, took all the money. And but he stayed then in at Yerkes for a couple of years, and he studied spectroscopy. And he also stayed a bit and worked at Mount Wilson with the newly the big telescope that was just finished over there. And there he met his future wife, Dorothy Block. And here's a lovely picture I got of their engagement just in front of Yerkes Observatory on an ox wagon. So that was an interesting engagement. And then in 1923, Harlow Shapley of Harvard invited him in, and presented him the post of becoming the director of the Boyden Observatory in Arequipa in Peru, which he accepted. And his main task was to start looking for an alternative place for this station. The official reason was that Harlow Shapley was not satisfied with the weather of Arequipa in Peru at the time, but the real reason I found out much later is that Harlow Shapley was fed up for the corrupt Peruvian officials that wanted him to pay bribe money so that he can import his instruments. So Paschavopoulos took a few trips to Chile and some of the deserts there to find a place. But Harlow Shapley, oh yes, Paschavopoulos on the porch of the house at Arequipa. He was a very serious man, as you can see. And here he is in the library again. And then Harlow Shapley decided that Bloemfontein will be the next station for the Harvard Southern Observatory. And here you can see with steam lorries, they're bringing the equipment all the way up the hill. And there they downloading the 16-inch tube, the big telescope that Paschavopoulos loved so much. And there they're busy, they just completed the dome's frame. And yeah, again, the serious moment. He's the man at the wheel. Paschavopoulos had almost completed 60-inch telescope. And there's an aerial photo. And there on top you can see the 60-inch telescope still being built. This is 1930. And there's Paschavopoulos is on the Newtonian focus of the 60-inch, and he's busy with a photographic plate exchange there. And there's another photo of him with the Bruce telescope, the 24-inch Bruce doublet telescope. This must be somewhere in 1948. I think this is Michael Bester. He was the observer at Boyden Observatory for 38 years. That one is, his surname was King from Harvard, who did his research there. There's Stoy from the university, from the Cape Colony Observatory, and there's Paschavopoulos just posing in front of the telescope. Here's another photo. That's an old photo. This is the 1930s with some of the assistants at Boyden at the famous steps in front of the main building's door. And there's Paschavopoulos and his wife, Dorothy. And this is the library now. What we have of Paschavopoulos personal items is this library over here. There's a little plate there that says this library is being donated to the Boyden Observatory's library. So this is all Paskevopoulos' personal books. Each of them has got a stamp. He had a Paskevopoulos library stamp. And some of the books are also that belong to Dorothy, his wife. So it's very precious to us to have that library. I've just cataloged it. If you want to, I'll send you the catalog of the books. Then you can see exactly what kind of books he was interested in and how old they are. So they're very valuable books indeed. And then I discovered this two scrapbooks of Paskevopoulos that he used to put in the newspapers articles in that he featured in. So he had a lot to say in newspapers at the time. He discussed astronomical and even Darwinism, and he liked to write articles in newspapers. This one is then in Spanish, while it was still in Arequipa, and then there he stands in top of the master's code copy just before Boyden was built, and he was quite amazed that our municipality gave him the land for free. So he didn't, and even later on the electricity and the water and sanitation and so on, all for free. So we, as people of Bloemfontein, welcome the observatory, as we did with the Lamont-Hasse Observatory on top of Naval Hill that belonged to the University of Michigan, which was built a year later. So this is about 1927. I believe there's a temporary shelter for the Metcalfe 10-inch telescope, 10-inch telescope triple. And here's some of the other articles. A lot of articles in this scrapbooks of him. I'm still to go through them. And some of them, of course, in Greek. So maybe I'll send it to you guys to translate it for me sometime. But this is one, I don't know which newspaper that is, but this is one that is the Bruce 24-inch telescope at Boyden. So he made sure that people in Greece knew about what he was doing in Southern Africa. And this is their way, on your way here. So on one of the steamliners, they had these pictures of the important people that were on board, and Mr. and Mrs. Paskevopoulos was one of the more important people. Incidentally, Dorothy was also a computer at the Harvard College Observatory, one of Edward Pickering's computer ladies. And this is another interesting photo I got there. This is Paskevopoulos at top of the Newtonian focus of the 16-inch telescope. And then this is one of the few jobs of the time that you can do laying down. And there he is having a lucky rest, a nice rest story underneath the 24-inch telescope. And that was the good old days that you can do the work in that way. And there he stands in front of the dome of the 16-inch telescope. And this is another picture of one of his articles. They are expecting the mirror of the new ADH Amberg, Danzig and Harvard 36-inch telescope that was installed there. Now there we have Eric Burton, that was the engineer of the time, and then one of the helpers there, the assistants, Victor was his surname, Bart Bock of Harvard College Observatory, and Paskevopoulos here at the right. And that's a picture taken just after the telescope was installed in 1950, December the 7th, they write the next morning after the first light. And there you can see Paskevopoulos and Bart Bock again, and one of our astronomers, Cellier, standing on that side. Unfortunately, this telescope was dismantled in the 70s somewhere. And just interesting to note that this was the world's first international telescope. The first telescope that had international partners. It was the Observatory of Amberg, the Observatory of Danzig, and Harvard College Observatory. And a few years later, the Boyden Council was established. That was after Pascoe-Wopler's death. And that will also be the first international observatory in the world. Right, then we have, of course, a few photos again of Pascoe-Wopler. He liked photos, I can see. But this is also a Spanish one. And then Pascoe-Wopler also discovered a few comets. This is one of them, the Pascoe-Wopler. I can't remember the number of this one. And then there's a lunar crater named after him, the Pascoe-Wopler crater. And then we also, in 2006, we had a chance to name 4 asteroids that was discovered at Boyden. And Professor Hoffmann decided to name Pascoe-Wopler after one of them. And here you can see a plate taken by the ADH, that Armagh-Danzig and Harvard telescope, on 10th of August 1966. And on this plate, you can find all 4 the asteroids that we could name. And there, that little one, that is the Pascoe-Wopler asteroid. Right, then interesting state, what happened to the old station in Arequipa? Well, I've got good news. It was given to a sister order of the Catholic Church, and they live there now. And this is comparison photos of what it looked like in those days and what it looks like today. One of my friends lived nearby, Javier Ramirez, and he come over there, and he had this notion to declare this a national heritage site for Peru, which was accepted by the Peruvian government. So no development can take place there, but there you can see just what it looks like today. That is the dome now of the 24-inch Bruce telescope. And oops. Oh, sorry for that. This is what it looks like today. This is the Bruce telescope's dome and building, and today they made it into a church, a small church. Now that is too beautiful, isn't it? So the dome is gone, but still it is intact as it was. There it is. There's the Bruce telescope inside, but they've converted into a chapel. There's the house. Also much in the state it was, and inside, in comparison, it is well preserved. Okay, then some of the photos were put over each other, the new one and the old one. So there you can see what it looked like way back, and more or less what it looks like today. So, well, I've got good news. It has been well preserved. All right, I think we've got a little video for you. This was now the Pascoe-Wopler part of the talk. We're going to show you now a little video to give you an overview of the museum and what we're doing at Boyden in these days. So just a minute, I just want to put on the video.
Thank you very much, Mr. van Jaarsveld. We are not seeing the video currently. We are just waiting a bit for Mr. van Jaarsveld's video. So if you can just be patient, I see that they're almost ready to show it. Thank you very much. We are currently not hearing any audio from the video. So
Is he nog on mute? Can you prop?
if you can maybe share the audio of the video, otherwise we can go over to questions. If there's any questions from the public side, please send to us in our chat box here on Zoom, or you're also welcome on the YouTube link to send us questions there, which you have for Mr. van Jaarsveld.
Lucas, can you hear me?
Yes, we can hear you now. We don't have any audio from the video.
Okay, I will somewhat give the audio as we go on. Okay, this is the Alvin Clark 13-inch telescope, and this is the exhibit inside the telescope. It is an interesting and a very important instrument in the history of astronomy. it took the very first pictures of Mars in the year in May of 1888 by William Pickering. And this is the Metcalfe triplet 10-inch telescope. Now, it was dubbed by Harlow Shapley as the most productive telescope in the 18th century, in the early 19th century. And this is a library which I just showed you. We are busy cataloging all the books in this library for an exhibit. So we will have an exhibit early next year. We also have a collection of the Harvard annuals from 1856 up to 1956. So it's about 100 years from the very first one. And this is a very interesting and valuable collection. All Harvard's observatories research were published in that annuals. Then we have also a collection of photographic plates, and then also a collection of atlases. And this one is a hand-drawn atlas by Schmidt, was his surname, from Germany, from 1840, of the moon. And then the glass universe you see here is the first photographic atlas of the whole sky taken by Harvard College Observatory in 1903. It's 55 plates, and which it would be sold for $15. There, the plates are in sequence like a puzzle. All the plates are also scanned and explained on the little computer we have there on the table, so the people can see these plates in detail. And then two of our old telescopes. This is a Benjamin Dancer telescope and the Steinhall telescope of the 1870s that was donated to us. Alexander Roberts was a missionary from Scotland in the Eastern Cape. He was a prolific variable star observer. He made 70,000 observations with that little 3.5-inch Ross telescope from 1838. We have his whole library and all his papers, which is now being digitized after a grant was given to us by the British Library. He was the only one at the time that did this research in the Southern Hemisphere, so that research is very valuable, and all has been donated to the Boyden Observatory. And then this is the exhibit of Earl Schleifer. He was from Lowell Observatory, and there's the camera that he used in 1939 to take the very first pictures, color pictures of Mars. So there the camera is attached to the Lamont-Hassey 27-inch telescope. And he also took 60,000 of the pictures of Mars in 3 years from 1939, 52 and 54. And this is a telescope they used, which was on top of Naval Hill, the Michigan 24-inch telescope. This is the exhibit for the Lamont-Hassey telescope observatory. Rossiter from Michigan used this telescope for 25 years to study double stars. And if you look on the ceiling, you will see what it would have looked like about 60 years ago. You look through the opening of the dome, and there you will see the telescope looking at Mars. And this is also a 3D picture of the telescope. The telescope is being re-erected, standing in front of the dome. Here you see a time lapse of that process. The telescope was in the veld for about 40 years. And then we took it back to its former home. And as a statue, it's now standing there, showing the public what was inside the dome. Inside the dome now, we have the Naval Hill Digital Planetarium. So it is a wonderful way to use the old Lamont-Hassey dome. as from stars outside the dome. Now we use it as for stars inside the dome. The lenses of the telescope were sent back to Michigan, but we then used the mount and the tube as a statue for the former days. Now this is the common mirror. Now this mirror has a very interesting history. It was used to build the biggest telescope in the world in 1890 by Ainsley Common in his backyard. Now imagine building the biggest telescope in the world in your backyard in Ealing, just outside London. Then Harvard bought the telescope from his estate, and it was used in the 16th telescope here at Boyden for the first time. It was used professionally, and underneath you can see all the instruments that was used in the on the Newtonian focus, spectrograph, photographic polarimeter, and the secondary mirror. And on the ceiling, we have some photos that was taken using this mirror, and we compare it with the Hubble photos of today. And this is a 60-inch today. There's Saki van der Westhuizen of the astrophysics part of our Department of Physics is opening the slit for the telescope. And it's been used now by the University of the Free State's Department of Physics. And a new spectrograph is also being built on this moment so that we can use it extensively for research in the future. All right, that is about the end of this video. Sorry for the hiccup we had with the technology. It must be the clouds, I'm sure of that. So if you have any questions, you can ask, and then we will try to answer it.
Thank you very much, Mr. van Jaarsveld. I've now checked on the chat. There isn't any specific questions. You are more than welcome to ask questions if you want to. In the meantime, I have a few questions from my side for Mr. van Jaarsveld. Nothing too serious, but just for interest's sake, you mentioned the Boyden Library. Is there any interesting books in the library that is not available, which is quite unique to this library?
Yes, we have books that belong to Edward Pickering himself, which he used to make a lot of notes in, which is wonderful. He was the greatest astronomer of his time in the early 20th century. So that you will find nowhere else. Then we have books that belong to Annie Jump Cannon with notes in it, and also books that belong to Henrietta Leavitt. For those of you who do not know, she was responsible to discover the luminosity period law that gave the astronomers later on the tools to measure the distances to stars and to find out that there are many galaxies outside the Milky Way. So that is important. Also very old books. The oldest one, I think, is 1799. And there are many of them. It belonged to the Phillips Library of Harvard College Observatory. And it was left here. And now we will take good care of it. There's also the atlases that I mentioned, many of them hand-drawn. And then we have also we've got the first photographic atlas of the Magellanic Clouds. The very first photographic atlas, it was taken from Boyden Observatory with the ADH telescope. And furthermore, we've got also, like I said, the first photographic atlas of the whole sky, the 55 plates, and a lot of other atlases as well. So if you watch, you can keep your eye on our Facebook next year when we have, when we come back, we will display this in a exhibit and in the library. So you you will see that, and we will make a video of that as well. Thank you, Lucas.
Thank you very much to you, Mr. Davy van Jaarsveld of the Boyden Observatory. If there's no questions, then we're going to move on to our next speaker for this evening. It is Professor Pieter Meintjes of the Department of Physics. Now, Prof. Meintjes is one of South Africa's leading physicists in the field of high energy astrophysics. He's also a member of the HES Consortium Research Group. He spent a postdoctoral year at the Max Planck Institute for Space Science in Germany. He serves currently on the executive committee of the National Astrophysics and Space Science Program and is often a visiting lecturer on astrophysics at the University of Cape Town. He is also a member of the management committee of the SA Gamma Consortium, a research cooperation between 4 universities in South Africa and also the NRF. This program is aimed at the development of high energy astrophysics in Southern Africa. Prof. Meintjes, the floor is yours. Can you hear me?
Yes, Lucas, I can hear you. Can you hear me?
Yes, we hear you loudly and clearly, and we can also see your PowerPoint presentation on the screen share. Thank you very much.
Okay. Thank you very much for this opportunity. So my task in this very special event is to introduce you to the 2 planets, Jupiter and Saturn. The properties of these 2 planets were briefly mentioned by earlier presenters. So I'm going to be going to show you a little bit more detail, although I don't want to lengthen the program too much. So I will keep an eye on the clock as well, because I have a tendency to go a little bit over my time, and I apologize for that if that happens. Okay, so the 2 planets, they were named after the Roman god Jupiter and also Saturn. Saturn was the father of Jupiter. So Jupiter was the god of the sky, and obviously his Greek association is Zeus. Saturn is also known as the god of time or the god of harvest, and his Greek name is Kronos because of his association with time. And like I've mentioned also earlier, he was the father of Jupiter. Before I step off this slide, the other name of Jupiter is Jove. And that is why these planets are also sometimes called the Jovian planets. So where will you find them? Jupiter is the 5th, and Saturn the 6th planet in the solar system. They are both gas giants, and there are other gas giants further away, Uranus and Neptune. And the planets closest or inside the orbit of Jupiter, they are more the rocky planets, Mercury, Venus, Earth, and Mars. So this is sort of a family portrait of the big planets in the solar system. I'm just going to focus on Jupiter and Saturn. You can see Saturn is this beautiful planet with the very prominent ring system. And this is Jupiter, the biggest planet in the solar system, with an orbital period of about close to 10 hours. And Saturn also with an orbital period just below 11 hours. And this fast rotation of these 2 planets play a very important role in the properties that I will outline a little bit later. So how did it all start? Obviously, the solar system started when a big star exploded in our part of the Milky Way galaxy before 5 billion years ago. And this gas cloud contains all the elements that were produced by the star that have exploded. And obviously that explosion enriched this region with heavy elements. As a result of the rotation, the cloud sort of panned out in a disk-like structure with the new star, the proto-sun, that was sort of gaining heat in the central part of that disk. And as time elapsed, the accretion of material onto bigger objects formed the new planets like Earth and Venus, mostly in the inner parts of that protoplanetary disk, with the gas giants more towards the outside. So when the new star started to burn hydrogen into helium, and when it produced an enormous amount of radiation pressure, the gas and lighter elements were sort of blown towards the outer parts of this disk where the gas giants formed. Let me just try to, looks like my scroll option is not playing along this evening. So like I've mentioned earlier, when the new star started to produce an enormous amount of radiation pressure, the lighter elements were sort of blown towards the outer parts of that protoplanetary disk where the temperatures were cold enough for these elements to stay intact without dissociating. So that is why you could find ammonia and methane here in the outer parts of that protoplanetary disk, where the planets like Jupiter and Saturn and all the other planets, Neptune and Uranus, condensed out of that material. So if you compare the density of the planets in the solar system and you compare it with water, with a density of 1 gram per cubic centimeter, one can see that the denser, the rocky planets can be found here in the inner parts of the solar system. And Jupiter, Saturn, Uranus, and Neptune in the outer parts of the solar system. You can see the density of Jupiter is just slightly higher than the density of water, while the density of Saturn is just slightly less than the density of water. So that means that if you can find a volume of water big enough that an object with the same density as Saturn can obviously float on water. So that is just sort of a comparison of the densities of Jupiter and Saturn with that of water. So the Jovian world, so that the gas giants in this radius versus mass diagram can be found mostly in this region. So this graph basically shows the radius as a function of mass of the rocky planets, the rocky worlds, that's called also the Terran worlds, then also the Neptunian worlds. So that is how the radius scale with mass of the planets like Uranus and Neptune, and the gas giants like Saturn and Jupiter have this particular radius mass relationship. And if you go higher up in mass, obviously you are entering the realm of the stars. So is our solar system unique? No. Star formation and planetary system formation occurs all over the Milky Way and all over the universe. This is a Hubble Space Telescope photo of the Orion Nebula, and showing protostellar disk with protostars that are being forming at the moment in the Orion Nebula. So what you see there, if I can point to this one here at the lower right, that bright dot there is the new protostar that is heating up, producing a lot of infrared radiation. And that dark band around it is the disk where new planets are going to form eventually. So star formation and planet formation occurs continuously in the universe, and our solar system is not unique. So this is just another view of that photo of some protostellar objects in Orion Nebula. And you can see also that the total mass of this material in the disk is about 0.01 to 0.1 solar masses. And in that material, the planets in these systems will form eventually. So since the two main characters in this evening's presentation is Jupiter and Saturn, I have here a picture of the comparative sizes of Jupiter and Saturn when you compare it to the other planets, Uranus and Neptune. You can see Earth is tiny compared to Jupiter and Saturn, as well as the other rocky planets. So this is sort of a profile of Jupiter, just giving its mass and also other important parameters. I'm not going to show everything. Jupiter is about 300 times heavier than Earth. It has quite a large number of moons. Well, the most recent number, as far as I could gather, is about 79. But still needs to be confirmed. The notable moons, Io, Europa, Ganymede, and Callisto, they were obviously observed first by Galileo Galilei here in 1610, when he pointed his telescope to the stars. Distance of Jupiter, 5 astronomical units, orbital period about 12 years, and surface temperature quite low, minus 100 degrees Celsius. Saturn weighs about 95 times more than Earth. It has probably about 82 moons, still needs to be confirmed. Notable or familiar ones, Titan, Rhea, and Pallades. It has about 30 rings in 7 groups. And the distance from the Sun is about close to 10 astronomical units, with an orbital period of about 30 years or so, and the surface temperature of about minus 140 degrees Celsius. So like I've mentioned, these planets, actually the moons of Jupiter, were first observed around 1610, when Galileo Galilei pointed his telescope towards the sky. And he was also the first to see and observe the rings of Saturn with that small telescope of his. Okay, today, if we look at Jupiter, the 4 Galilean moons like Europa, Io, Callisto, and Ganymede can be found reasonably close by compared to all other planets. So they are the most prominent and the biggest planets of Jupiter. Like I've mentioned, Jupiter probably has around 79 moons. Many are very small, just big rocks, basically, like Ananke. Ananke, if you look there at that photograph, is that tiny light dot there is one of the very small moons of Jupiter, and I named my daughter after this little moon. And this is a picture of Ananke. Saturn, on the other hand, has also a large number of moons. And obviously the most prominent of its moons is Titan, who also incidentally have a thick atmosphere, much like the atmosphere of Earth. So they are the most massive planets in the solar system. So they contain basically most of the planetary mass in the solar system. So each of them is composed of roughly 70% hydrogen, 24% helium, and 5% of all the other planet elements by mass, obviously heavier than helium. We call them metals in astronomy. And both these planets rotate quite rapidly. So they are noticeably flattened or oblate. So if you have a fluid body like a gaseous planet like Jupiter or Saturn, and you let it rotate quite rapidly, obviously it's going to become sort of elliptical in shape. The smaller the nucleus of that fluid mass compared to the total volume, obviously the more oblate it will be. So if you have a rotating object with a big nucleus or core, then obviously it will be more spherical than an object spinning at the same rate but with a smaller core. So the oblateness basically give us a measure to gauge how big the core of that gas planet is. So like I've mentioned, both these gas planets, Jupiter and Saturn, are quite oblate. So, and they must obviously spin very rapidly. So they have a very small core compared to the total volume of the planet itself. Another property of these two planets is that they rotate differentially. So what is differential rotation? If you compare it to solid body rotation, like let's say, for example, a snooker ball or a solid object that spins, obviously each part spin at the same rate. It is different for, let's say, a volume of fluid that rotates differentially. So it means that particles in the fluid at different distances from the axis of rotation rotate at different velocities. That is what differential rotation means. So like I've mentioned, the oblateness of these two planets basically tell us how big the core is of that planet in relation to the rest of that planet. So Jupiter probably has a rocky core several times more massive than Earth. So the core is surrounded by a layer of liquid ices like water, ammonia, and methane. So on top of this is a layer of helium and liquid metallic hydrogen. And obviously the internal structure is similar to Saturn's internal structure is similar to that of Jupiter, but its core makes up a larger fraction of its volume, and its liquid metallic hydrogen mantle is also shallower than that of Jupiter. Now, here on the left, you can find a graph of temperature versus pressure of a gas like hydrogen. And you can see that depending on what the temperature and pressure is, a gas like hydrogen can exist in different states. It can, in some place, it can exist as a gas. Another place, in terms of temperature and pressure, it can exist as a liquid. And then obviously it can also exist as a metal. So why do we call a gas a metal? So the reason why it's called metallic hydrogen under extreme pressures is that the electrons in that material are free to move like those in a metal. That means you have a very, very good electrical conductor. So hydrogen under extreme pressures can be a very good conductor of electricity, and this plays a very important role in the generation of the magnetic field of both Jupiter and Saturn. So this is another picture of the internal structure of these two gas giants. You can see this dark pink zone here is where you have the metallic hydrogen, hydrogen under extreme pressure. So it means that the electrons in the hydrogen are free to move through the crystalline structure. And this obviously helps with the generation of enormous electrical currents that can generate a strong magnetic field. Similarly, also for Saturn, you can see that there is that zone with the metallic hydrogen, and there is the core of the planet Saturn. Here you can also see the rings of Saturn, but I will say more about that a little bit later. So here is a nice, two nice views of the atmospheres of Jupiter and Saturn. So the visible surfaces of Jupiter and Saturn are actually the tops of the clouds. Actually, that is what we call the surface of the planets. It's basically the cloud tops of both Jupiter and Saturn. So the rapid rotation of the planets twists the clouds into dark belts and light zones that run parallel to the equator. So this bands of clouds that you are seeing here is basically dragged on by the rapid rotation of these two planets. You can see the same thing also there in Saturn. So the outer layers of both planets, the atmosphere, show differential rotation that I mentioned earlier. So the equatorial regions rotate slightly faster also than the polar regions. So here at the equator, the rotation rate is more rapidly, is faster than there closer to the poles. So the polar rotation, so the rotation rate here in the atmosphere at the polar regions for both Jupiter and Saturn is actually very close to the internal rotation rate of the planet inside. So here we have a view of the atmosphere of Jupiter. You can see the bands of clouds that are moving at enormous velocities, about 500 kilometers per hour, as a result of the rapid rotation. You can also see the famous red spot of Jupiter, which is a notorious high pressure system that is now visible for more than 350 years or so. So here on Earth, we also have these cyclones. That is what you can call that red spot of Jupiter. Is actually nothing else than a cyclone. And due to the laws of fluid dynamics, one can actually predict here on Earth basically the effect of the Coriolis force or the Coriolis effect. What that effect will be on winds that circulate the planet. So obviously, in terms of the laws of fluid mechanics, one can see that for low pressure cells, that equation that you see there at the top, which we call the geostrophic approximation, actually predicts that for low pressure cells, you will have an anticyclonic rotation or anti-clockwise rotation here on Earth. While for high pressure systems, you will have a cyclonic or clockwise rotation around these high pressure cells. Now, unfortunately, for Jupiter, the total opposite happens. For high pressure systems like this red spot, the rotation is basically anticyclonic, and it's not quite understood why this is so, why it is different than here on Earth. But recent computer simulations have done only recently start to reproduce these type of results.
Sorry, Prof. Mankies, I just need to jump in here. I've been informed that we have images that is coming from Centurion of the conjunction event. It's a very small window, unfortunately, we have due to the weather. So, Prof. Hoffmann, can you maybe give us an update regarding the live images?
Oh, thanks, Pete Mikey, so far. Unfortunately, we have only a few official minutes on the broadcast. I hope we can stretch it a little bit. We are waiting for Clyde Foster to be allowed into the Zoom meeting. Manolis, if your guys can just attend to that. He has a live feed from Pretoria. There's a short uncloudy window there. On the chat, I have shared his email address. So if you can attend to get him into the meeting. So I'm now going to quickly share my screen here. Okay, so can you guys hear me?
Yes, we can hear Prof.
Okay, I can't share yet. If you can make me co-host so that I can share. Okay, now let's see. I will soon also get in some response, some information from our colleagues there at Boyden Observatory, but I will just start now with how we observed the conjunction event on Saturday evening with a video produced by Piet Leroux from the Astronomical Society of South Africa. Now let's hope I get it going quickly. Can you guys see the video? Patricia, kan julle dit sien daar?
We see a video from Mr. Clyde Foster.
Wow, fantastic. Okay. Let me just then close here. Okay, Manolis, I closed my video now. Okay. Clyde Foster, there's Clyde. Okay. Excellent.
Hi, Marty.
Yes.
Oh, this is live, right?
Can you hear me?
Yes, now we can get the full screen of your view there and you can explain to us.
Yeah, and I've got a capture failure. So let me just try and sort this out, Marty. I'm just going to restart. Just hold on a second.
Okay. Just as information for our audience, Clyde Foster is a retired chemical engineer.
Okay. Are you seeing that, Marty?
I see something there, looks a bit like Saturn. I see one, and I see a moon there. I don't see two objects yet, but maybe you can pan. Okay, while Clyde is working there, just to mention, Clyde is dedicated planetary photographer. We will share more information on him as time allows. I will just want to mention while Clyde is working on his image feed, in the chat, I have also shared a live feed link.
Okay, so I must share my screen, Marty.
Yes, you should share your screen. Okay, Clyde, on your screen. Okay, start the screen sharing. Excellent, Clyde, we see now. Well.
Got it.
Okay, Clyde, you can explain, say a little bit about your setup there. Okay, the screen appeared and disappeared again.
Okay. Yeah, I think Peter shared a screen from what I re-share my screen.
There it is.
Okay, so obviously we've got Jupiter up at the top, which is overexposed at this stage, and but Saturn is showing quite nicely down at the bottom. So if we increase a little bit, then okay, then you've got the four moons of Jupiter up at the top there. Are you able to see them?
Fantastic, Clyde. It's so thrilling to see the 4 moons. Can I ask you a question?
Yes.
Okay. If you take the angular size of Jupiter that you will know from your planetary photography work and take that as a reference to estimate the angular separation of Jupiter and Saturn.
Okay, Jupiter at the moment is 33.3 arc seconds. So I'm just trying to get something to measure quickly with Marty. Let me just get an indication. So yeah, roughly you're talking 1, 2, 3, 4. Yeah, about 4, maybe 4.5 diameters of Jupiter. So what? 4.5 times 33 seconds.
So that gives us a small fraction, less than 0.1 degree.
Yeah, so it's meant to be 6 arc minutes. So that would be so that's about 360 arc seconds. So I would expect the gap to be sure. So it actually looks a little bit closer to me.
That's a good idea. So that's 0.1 arc minute, the diameter of Jupiter.
Jupiter is 33 arc seconds.
Yeah, so that is rather 0.5 arc minute. Okay, then
okay, and let me just drop. I'm going to drop the exposure a little bit.
Yeah, that's an interesting comment.
To try and get a better view of Jupiter.
Yeah, that's correct. Just a comment. You can go and Google it. A few months ago, there were great excitement in the Astronomical Society of South Africa and the amateur astronomical community in the world, because Clyde Foster, not being a professional astronomer, but a very, well, let's call it professional amateur astronomer, discovered a new spot on Jupiter that got named after him, Clyde's spot. So we're just proud that we have people like that participating. Clyde, if you can just mention briefly something about your observatory and your equipment, and then we can
Marty, yeah, just in terms of the view at the moment, I've obviously dropped the exposures and everything, so you can start picking up on the belts of Jupiter there. Obviously, Saturn is quite faint, but can you still see that okay?
Saturn is quite dim here at the bottom, so you can maybe take up your exposure a bit.
Okay, but with Jupiter, can you see start seeing the belts? I don't know how clearly it's coming across.
We can, yes. We can just see the belt. I assume that Jupiter is now about 15 degrees or 10 degrees above the horizon. So we look.
It's getting down towards my neighbor's garage roof.
Yeah. Okay, I see they want us to speak a little bit closer to the computer so that they can hear more clearly. Okay, lastly, Clyde, what equipment are you using?
Is that a bit better, Marty?
Yes, there I can even see Saturn's ring now.
Yes. And the belts of Jupiter, obviously the seeing conditions like this are very, very poor. Marty?
Yeah, one can assume that, but we have them in one telescope view.
Sorry, I'm just doing a quick capture because this is about the only opportunity I'm going to get to be able to. Yep.
Okay, I hope you are recording for the sake of history, or I think the Zoom administrator will also be recording. Okay, now let's see our colleagues at Boyden Observatory. I don't see them here on the list at the moment. I'm quickly going, if they can make me co-host, just share something here. Manolis, if you can allow me.
Just tell me when you want me to stop sharing.
I think you can stop sharing now. Fantastic, Clyde. That was a high point to have it in real time from South Africa.
Absolutely, yeah, very, very exciting, Marty. And I think you know what Jupiter and Saturn and Mars mean to me. So to see these two like this are very, very, very special.
That's true. Okay, we are very close to the end of our program. So let's just share some information. Also, there will be other live feed links that I have already shared in the chat that people can go and proceed on their own time. It's getting dark now, almost in Cape Town, in about 15 minutes. And apparently, Martin Lyons from Cape Town, they will be observing the conjunction event from there. Okay, now, if Clyde, if you can stop your share screen, and if Manolis can enable me then just quickly to share some information here. Manolis, can you hear me? Am I? But I can't share. Okay, julle.
I'm Marty.
Hello, Clyde. Like apparently everyone disappeared. Maybe the event concluded.
No, I can hear you here from Greece. This is Vasilis.
Okay. If someone can just enable me to share. I don't know why I can't share my...
Okay, am I still sharing, Marty? I can't see on my screen here.
Yeah, I think they should abort your share now.
Give me a moment. I am making a co-host.
Thank you.
Okay, I think that now you may be able to share the screen.
Okay. Yes, right. Okay, just to conclude, you can see there we have observed the real footage. The orientations were not always the same, depending on orientations of cameras and so on. Here is a diagram that our postgraduate student got from Stellarium, just showing the configuration of Jupiter, Saturn, and some of the moons. You will recognize the moons that we saw on Clyde Foster's image. Then there will be the conjunction live feed from Cape Town. Those links, there's a Skype link for discussion participation, and also the live skies of Martin Lyons. Those are in the chat discussion. And now let me then conclude. Just ask my Biden colleagues, Tinus Pitleroux, are you there? Can you come in? Okay, I don't get reaction from them yet. Okay, let me just then go to another last share window from my side.
Can you hear me?
Yes, we can hear you.
There was a question at some point if we can keep the Zoom open until after 8 o'clock.
Yeah, if you can keep the Zoom up a little bit.
Yes. We'll keep it for 15, 20 minutes or so. We can do it. Yes, of course.
Share screen. Okay, now I go to.
Okay.
Ik ga nou klaarmaak. Okay, that's the last thing that I wanted to share, just to show you in real time what's happening out there where Jupiter is now. You can see the distance, and you see how it is changing. So how it is moving through space. You can actually see here animation of how it is also moving through space, but just to show there that every few seconds the distance changes with a kilometer or so. Okay, so with that image, I'm going to conclude my abort my share.
Okay.
Or Manolis, you can abort my share from that side. I don't. Okay, there it is. Stop share. Okay, Tinus.
Hello, Marty.
Hello. Okay, can you just quickly say what we did on Saturday evening?
Marty, yes. On Saturday evening we did a sort of a test run in which the two planets were still quite far apart. Pete LaRue actually used his telescope and camera at that stage, and we set up a method to actually do this stream online, and it worked quite well. At that stage, of course, that was two nights ago, and we had very nice clear skies. I think he did take a little video which he sent to you, and you can maybe share if you can get hold of it again. So that we can actually also then see the difference between the images on Saturday and today. But unfortunately today has been, since about 5 o'clock, completely overcasted in Bloemfontein. We didn't even see the sun set, which is normally not the case. From Boyden you have these very beautiful sunsets, and we didn't even see that. We can't see the moon, there's nothing, it's just clouds. So unfortunately the whole show has been closed to us, but that's why we are very fortunate to have this these beautiful images from Clyde.
Okay, I hope you can still hear me. Manolis, if you can just quickly allow me a last screen. I just want to a last share screen so that I can share the footage that we recorded on Saturday evening.
Yes, of course. You can share your screen, yes.
Kan jullie zien nou? Kan jullie zien wat ik share?
We can't see anything, Marty. We just see your folder there. It's not opened. Just open the file.
Yes, yes.
Okay, I think you can see the view now. Is that correct? Can you guys see the recorded footage from Saturday evening?
No.
No, we cannot yet see it, Prof.
If you double click on it, maybe we will be able to. I don't know.
Share, probeer dit, share screen. Okay, so ek moet, okay, wat ek moet doen is ek moet hom eers gaan oopmaak. Okay, just give me a moment.
Professor Hoffmann, we cannot see your screen right now. Okay,
is it there now?
Yes, yes, perfect. Thank you.
Okay, so there is the footage that we obtained on Saturday evening, and by comparison with what we saw from Clyde's share a few minutes ago, just compare the distance. You can see the Jupiter there and Saturn much further. So actually between Saturday, the last 2 days, the approach, Saturn moved about to that position, about a third of the distance that it was on Saturday evening. Okay, I think with that contribution that we obtained from Boyden Observatory with the assistance of the Astronomical Society of South Africa, we can conclude the official part. Remember to go and look in the chat view. If you can keep the Zoom session open for a few more minutes, that people that want to look at the feed from Cape Town can go and copy the links there. I'm glad that at least we got some live feed from South Africa with Clyde's assistance. Thank you for all the other efforts. And then I give back to our Greek colleagues, to Manolis and his colleagues, just to officially conclude our official broadcast.
So thank you very much, Professor Hoffmann. It was a great opportunity to see Boyden Observatory, your great work. We would like to thank you very much for sharing with us Saturday and today. As we discussed before, in Greece, things were a bit difficult. So we had to, we could not show any footage here. The clouds are too many outside. So, on behalf of the organizing team, we would like to thank all of you, all the speakers, all the colleagues from South Africa who were with us. And we really hope that we would like to thank Mr. Zadonakis, and we would like to thank Professor Hoffmann, Mrs. Patricia Lamus, and all the colleagues from the Boyden Observatory in the University of Free State who were with us today. We are looking forward to meeting with you and continuing our work together. Finally, I would, on behalf of the organizing team, I would like to thank every person for joining us in this 3-hour marathon. We try to convey the enthusiasm and the love we have for the skies, and we tried our best to explain this phenomenon. So, thank you all. And we will not close yet. We will stay for a few minutes to do a live feed from Cape Town. Okay. Or some, how do we do it, Professor? Should I share my screen? How do I do it?
I think they can. The one option, of course, is to just go to the chat. Near the end of the chat, there is the link liveskies.org, and you can copy it into your own browser and do it like that. I think that will be the easiest way. I don't know exactly how the full access will work there, but I've arranged with Martin Lyons, so he opens the link. That's a purpose. So there maybe just we'll need some concentration just to get entries. I will quickly WhatsApp him just to alert him that some people may join now from the audience that was part of this wonderful event.
Thank you very much. Thank you very much, Professor Harmandaris, for your kind words. We thank you for your inspiring presentation. I will try to share the screen now to see, not that cell, the other cell. So I will try to see what happens in Cape Town right now. As it seems, yes, live video of the conjunction in 20 minutes. So we are expecting it in about 5 minutes from now.
Okay, that's great that you can see it like that. Okay, so I think we can relax and enjoy a cup of coffee and just observe.
Okay, so thank you very much again for the great collaboration and this great meeting.
Okay. Thanks to all my colleagues for their excellent contributions and time. We have learned a lot, and there may be other astronomical events. We never know exactly what will happen when. We can just imagine what we would have been able to do in 1994 with the Shoemaker-Levy 9 and Jupiter event, if we had the technology that we have now. And things like that can happen again.
we think that this is a good moment to say goodbye for today. We would like to thank everyone for the participation. Any questions that have been sent to us via email shall be answered. Okay, so.
Manolis?
Hello.
Bye. We were together with all the stress of the technical things.
Bye-bye.
Practice. Okay. Bye-bye.
Bye.
Happy Christmas to all the participants. Thank you.